Welcome back. It's Monday here at Chemistry 2341, and we're going to continue on with we're going to finish out Module 1 today and do Module 2 on Wednesday and Friday. And so we should have almost all of Module 2 done. However, the homework for Module 2 will not be due until Monday at midnight, just to make sure we get through all of it. Okay, so administration, obviously you have found the new Zoom class. There will be a new Zoom at each week, so please look for that email on Monday morning. I might start sending them out Sunday morning or Sunday afternoon, just to make sure you have plenty of time to find your email and get that situated on your computer. We have logins for Top Hat. I have invited every student, and anybody who hadn't signed up, I've invited again. There's still a few people who have not accepted that, and I've talked to a couple that I've emailed, and I think we've gotten those taken care of, or they will be taken care of soon. But I have about 3 other people who haven't signed up, so maybe they've dropped the class, but if not, then we have 46 signed up. We have 48 in the course, so I think 2 of them might actually just be signing up today then. So that's great. So our Top Hat is going well. So on Wednesday, Thursday, and Friday, I'm going to assign mock tests so you can start testing out your computer with the testing function, which is that Proctorio add-on to Google Chrome. So make sure that you look at I'll send you a link to a site on Top Hat that shows you how to download the Proctorio add-on. It only works on Google Chrome, and it gives you some ideas about how to make it work best. For example, closing out all your other tabs, etc. I'll send out that email today, and so that we can start looking at doing just 5-minute test exams so that you have an opportunity to work out all the bugs and make sure you get all the settings just right, okay? So go ahead and start reviewing Module 2. That should have been released. Not only the slides, but also the reading assignment. And so when you do the reading assignment, it's best to kind of read along and try to answer the question. If you answered the question wrong, go ahead and read over that section again. So you're using it as kind of a self-testing tool as you go forward. So you're not just missing something and just trying to pile extra information on. So once you get that, you can just continue to go on. And then if you still have questions, go ahead, write that down and bring it to live class. We'll be able to discuss it here in live class. And if that's still troubling, go ahead and email me. We'll set up a one-on-one Zoom session where we can talk about that particular subject and maybe try to get a different perspective so that you understand it completely. Okay, let's see. So our homework for Module 1 is due midnight tonight. Our homework for Module 2 is due next Monday at midnight as well. Okay, any questions about administration so far?
I have a question about SI.
Yes.
So is there a way that you or Nick can send out like the schedule and like for the who's on what times? Because I think I'm not sure what time I think I signed up for Monday, but I'm not exactly sure what time it was.
Did you ever get a confirmation email from the SI department? It should have been received around Friday with a link specific to the session that you were assigned. If you can't for whatever reason, that's all right. Send me an email and I'll forward you to my supervisor. But I can also post, I'm making a flyer that has all the links to my sessions. The only issue is that we do kind of want you assigned to a specific session for the week so that they're all populated evenly. But yeah, like I said, send me an email if you can't find that confirmation email that you should have gotten around Friday.
The course syllabus?
I'm sorry?
Is your email in the course syllabus?
Yeah, and I'll put it in the chat right now too, just for everyone's safekeeping.
Yeah, and Nick, when you finish getting that schedule flyer that you were going to set up, go ahead and post that to Canvas as well in that open pages, okay?
Pages, all right. So just be on the lookout for that, and it'll be there as well for in the case that you can't attend the session you were supposed to.
I appreciate it. Thank you.
Yeah. So about Canvas, well, I've started posting things to Canvas, including slides if you're having trouble downloading them from Top Hat. I have a question and answer session with Top Hat today. Figure out why you can't download those. You should be able to, so that's what I'm hoping for. But I'm also posting them to Canvas the week that we're going to start them, so you don't just have them all downloaded. I might actually end up having them all early, but I don't yet. In addition to that, on Canvas, I've added a couple new pages, and the 2 pages in particular that'll take place that are important for module 2. Let's see. Not pages, I'm sorry, files. It's under files, not pages. There is a thing called Organic Nomenclature Review. Okay, go ahead and download that Organic Nomenclature Review. It's basically all the rules and everything we're going to learn about nomenclature. We're going to do most of these rules in module 2. However, we're going to add a few things as we go on. For example, when we start talking about carbocations, we're going to look at primary, secondary, tertiary carbons. But this gives you a great go-to sheet as you're learning your nomenclature. It gives you all your functional groups, it gives you hierarchy, it gives us the rules, it gives us the process, everything like that in one simple little place. So please download that and keep that handy as we go through the nomenclature chapter, which is module 2, which will start on Wednesday. Okay. So that's all the administration I have. And so I think we should continue with module 1 unless somebody has a question. Ooh, I got to admit somebody in the thing. There we go. Somebody was in the waiting room, so I had to admit them. So, okay, welcome, welcome. Okay, so if there are no more administration questions or chemistry questions, let's go ahead and move on to the last half of module 1, which is the physical properties. And then we're going to do the last module, which is called module 1.2, which is resonance structures. And I'm going to talk about resonance structures and why we use them and how they tie into Lewis dot structures. Okay, I'm going to go ahead and share my screen. And there's my screen. You should see something that says 3.3.1. And let me go ahead and move my grid over here so that I can watch it there. Okay, so we learned last time that we have certain intermolecular forces that we see in organic chemistry. We learned about 5 of them in particular, which is ion interaction, ion dipole interaction, hydrogen bonding, dipole-dipole interaction, and induced dipole, or London forces. And those are increasing and decreasing in order of strength. Okay, so because we have these different types of interactions available to us, and they have different strengths between this molecule and this molecule, that changes their physical properties. And we have physical properties that we are going to look at specifically on how they change are melting point, boiling point, and mixing solubility and or miscibility. Okay, and so we're going to look at all of those as a function of the intermolecular forces that allow them to do each of these different functions. Okay, so as we started with before, we have that melting point is basically just when molecules have enough energy to start moving past each other. Okay, in a solid, they tend to be stuck in a certain place and they just vibrate. They don't actually move, they just kind of vibrate, and they tend to be bonded to each other in a specific fashion. You have to have enough heat, enough energy to break those interactions between the different molecules, and so they start to move. And when they start to move, they become a liquid because they're no longer tied into a fixed state. They actually can move and tumble around. Okay, so in the strongest forces like ion-ion, we have a very high melting point. It takes a lot to break that ion-ion bond. Now, as we move down to hydrogen bonding, that's the next the ion dipole, but this is the next just molecular non-ion property we deal with, and it's hydrogen bonding, and it has the greatest effect on melting point, boiling points, and solubility of any of the others because it's the strongest interaction we have. Okay, So as we move away from things with hydrogens that can hydrogen bond, and those tend to be hydrogens on oxygens, sulfurs, and nitrogens, if we move away from that and we only have polar molecules, we have that dipole-dipole interaction. So the positive side of the molecule is attracted to the negative side of a different molecule, and that's the interaction we have. So that's a weaker interaction, and so there we see less of an effect on the boiling point and melting point as compared with hydrogen bonding or other ion bondings. Now, the weakest, of course, is our dispersion forces because it's barely charged at all, and it's very susceptible to the shape of the molecule. The London forces, the longer or the higher surface area you have on your non-polar molecules, the more likely they are to interact. Therefore, the more spherical your molecule is, the less it interacts with the things around it. And therefore, the London forces are controlled by the fact that there are no other forces, and so they have to induce a dipole, and their shape. So we'll see that again and again as our molecules change size, shape, and bonding types. Okay. So in contrast, we have boiling point. Okay, so boiling point is once we take a liquid and we have to have enough energy added to it. So there's typically a lot more energy added to the system such that it breaks all molecular forces, intermolecular forces, okay? Because when we're going from a solid to a liquid, there's still intermolecular forces in between these. We're losing all of that, and we actually are driving an individual molecule into the gas phase. So that's why it takes so much more energy. And in the case of the ion-ion interactions, this takes a lot of heat. And so our boiling points tend to be thousands when we have ion materials. Hydrogen bonding is not as, is the strongest of our non-ionic systems, and therefore it has the greatest effect on boiling point as well. So what we'll see here is things that can hydrogen bond tend to have higher boiling points. And the more hydrogen bonding units you add to a molecule, the higher the boiling point and melting point goes. Dipole-dipole interactions are next. And again, if you only have one dipole on a molecule, the positive side of one is attracted to the negative side of the other. And therefore, that's the major interaction we have here. And then when we go to those non-polar systems, they tend to have the lowest boiling points possible because they have very weak forces, and it's very easy to separate them and drive them into the gas phase. Okay, so, but boiling point is affected not only by the type of interaction, but how many of them you have, okay? So the more of a polar, if your molecule is small and has a dipole on it, then you have more likely to get that dipole-dipole interaction. As your molecule becomes increasingly non-polar by adding longer and longer chains on it, that dipole-dipole interaction is being affected less. And so what we end up seeing is the London forces start to take over, and our boiling points can go down. Okay, and so boiling point and the melting point, boiling point in particular, is affected by number one, molecular weight. Number two, the type of interaction it has. Okay, so a small polar molecule is likely to have that dipole-dipole force and have a higher boiling point than you expect it to have than a big molecule with no dipole-dipole interactions. So if we look at the series of molecules we have here, we have a fairly small molecular weight material here. This is dimethyl ether, and it actually boils below room temperature, okay? The only thing it has going for it is it has a dipole-dipole interaction between that oxygen, that partially positive oxygen, and those two the partially negative oxygen and the partially positive carbons near it, okay? So that's the only interaction we have, and it has a very low molecular weight. And so we have a small boiling point below room temperature. Now, just by adding a little bit of mass to there, our boiling point comes up. It's still below room temperature, but it comes up just by adding the mass. We haven't changed the intermolecular force, and we really haven't increased the amount of London forces available to it. So we see that the boiling point is coming up mostly because of the molecular weight. Now, by adding another carbon to it, we've increased the molecular weight again. Again, it only has that dipole-dipole force on it, and our molecular weight, our boiling point comes up just a little bit more. Okay, so now we in addition to having this dipole-dipole force, we now can start London forces in between these longer chains. And as those chains get longer, we have more and more London forces available to us. And therefore, by adding one more carbon, we see an increase in boiling point for partially the molecular weight, partially the dipole-dipole interaction, and partially the new, bigger London force because you have a longer non-polar chain. So boiling point and melting point are both affected by all of these different interactions and how they play together. And so we'll see that in certain compounds where they shouldn't have a high boiling point, but they do because of one or more of these interactions. Okay. So, and the classic example of that is water. Water has a molecular weight of 18. It should be a gas. However, it has two hydrogens that hydrogen bond, and it can hydrogen bond to two other atoms, two other molecules, and it can keep adding those forces together and together, and that gives the boiling point of water at 100 degrees C, which is probably 200 degrees higher than it should be if we were just looking at a non-polar equivalent to that water. It would be methane, which would be non-polar. So it's like 200 degrees higher boiling point than we see. Okay. I have a question in the Zoom chat here. It's, if you have a large molecule versus a hydrogen bonded small molecule, how can you tell which has the largest boiling point? Okay, that's a very good question. There is a break point as far as London forces versus hydrogen bonding. And as we go forward and as we look at new compounds, we'll see that after about 10 carbons or so, the London forces are equivalent to one hydrogen bond. And so, but usually we do it in a trend where you have similar sized molecules and they have different forces. So that's what you should be able to tell the difference is that the molecules, even though they all have a molecular weight of 50, the hydrogen bonding one is going to have the highest boiling point. The one with dipole-dipole interactions is going to be the intermediate one. And the one with the non-polar one is going to have the lowest boiling point. Does that answer your question? Hands raised. Okay. So London forces, all these different intramolecular forces affect our boiling point, our melting point, but it also affects our miscibility and solubility. So first of all, let's define miscibility. Miscibility means you have two liquids and that they either can be completely mixed in any combination possible. That is a completely miscible liquid. Okay, is that all of the water in vodka you can take vodka, this is my example, and you could have 100% alcohol and 100% water, and you can mix them in any portion possible. Okay, that is the definition of miscibility. Solubility is when you can get some of a liquid or solid dissolved in a solvent, but it cannot mix in any ratio possible, and therefore that's the subtle difference between miscibility and solubility. Now, most of the time when we look at things dissolving in things, we think about like dissolves like, which means if you have two compounds that hydrogen bond, they will tend to dissolve each other or dissolve in each other, okay? Then not necessarily miscible because there's other forces to take into account. But in the case of this example of ethanol and water, ethanol is small enough and hydrogen bonding is its major intermolecular force, and water is small and hydrogen bonding is also its major intermolecular force. Because they are both in that way, they are more likely to be miscible. However, as this chain grows, the London forces become more dominant. Okay, and we see that in other materials. So, for example, that only goes so far. So methanol is a small molecule, and it has hydrogen bonding as its major intramolecular force. So when we see that, if we look at the solubility in water, actually, let me change to a different color. There we go, blue, that's a good one for that. This is the little infinity mark here. It's infinitely soluble. And when we say infinitely soluble, that means it's miscible. Any combination, 100% methanol to 100% water and anything in between, it'll completely make one liquid mixture. Okay. However, this methanol, because methanol is, and the hydrogen bonding is its major intramolecular force, it dissolves very poorly in hexanes. Hexane is just your straight chain hydrocarbon with six carbons. And I drew it wrong, so I'm going to draw it again. And actually, let me draw it in red so we can differentiate between the two. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, so it's just a straight chain hydrocarbon, only carbon and hydrogens, and that's all we have. Okay, and its major driving force is London forces. Okay, so by increasing the length of our chain by 1, turning it into ethanol, we still have hydrogen bonding as a major function, but we have a slightly longer nonpolar tail to it, meaning it's infinitely soluble in hexane. Okay, so this is our balance between the hydrogen bonding as a major contributor to solubility, but London forces are starting to come into play because of our miscibility in the hexane. Let's add one more carbon right here. And so now we have this longer nonpolar chain, but we still have this strong hydrogen bonder, and we are still infinitely soluble in water. So it can be completely miscible, but it's still also completely soluble in hexane. Okay. Now we start to see a change. As we add that last carbon now, and so now we have 4 carbons here. So now the London forces are taking up a major portion of the surface area of the molecule. And so our solubility starts to drop in water because this whole side of the molecule does not want to dissolve in water, and therefore is not completely miscible. However, it is still, because now London forces are a major force, we are now getting into the infinite solubility. So as we go up again with just adding one more carbon and then another carbon here, we see increasingly less soluble in water, but still completely soluble in hexane. Once we get past this, the general rule for hydrogen bonding is about 4 to 5 carbons. You can get a single hydrogen bond to pull a hydrocarbon into water. Above that 4 carbon limit, it tends to be insoluble in water. Okay, and that's for each hydrogen bonding group. Okay, so the general rules, we have this miscibility.
Dr. Irving,
yes.
Question in the chat.
Oh, yeah. Oh, sorry. If you increase the temperature, will you increase the solubility of a longer carbon chains in H2O? Interestingly enough, it does change it slightly, but not significantly enough to break the rule. Once you get to that 4 or 5 carbon chain, it just doesn't want to be in water. It's too nonpolar and will not dissolve in water. There is a slight change in solubility, but not significant. Okay, thank you. All right, so this is kind of the summation of the different interactions available to us and whether or not things tend to dissolve in each other. And so what we can think of is that if we're using an ion as a solvent, most of the time our ions are solids at room temperature, and so we rarely use them as solvents. Okay, so that's why we say not applicable to these here. So if you have a hydrogen bonding solvent, think water, alcohol, they can dissolve ions quite well because that ion hydrogen bond or an ion dipole, they tend to be fairly soluble in that. And if you can think about it, all in inorganic chemistry, most of your salts dissolved in water. There were a few exceptions, but most of them did. Okay. Now, if you have something that's solute, is the thing that's dissolving into your solvent here. If you have something that hydrogen bonds, again, a thing that hydrogen bonds is typically very soluble in something that hydrogen bonds. Okay. If you're looking at dipole-dipole interactions, it kind of varies, because if it's a strong dipole and you have a hydrogen bonding solvent, that can act as a dipole, and they do go in sometimes. However, you can have a nonpolar side of a molecule which changes its solubility. So it can or cannot, and there's different cases where we'll see, oh, that should have dissolved in water, but it didn't. And then when we have induced dipole in a hydrogen bonding solvent, we tend to think it doesn't dissolve there because that hydrogen bonding is a fairly strong interaction. That induced dipole is a very weak interaction, and we typically don't see the induced dipole or nonpolar materials dissolving in hydrogen bonding solvents unless they're really small. With dipoles, you can actually get some ions to dissolve in things with dipoles, but it's not really a high concentration, and sometimes things just won't dissolve at all. You can imagine something like table salt won't dissolve in something like acetone. Acetone is a classic solvent we use, and it has its only interaction as dipole, but it won't dissolve something like table salt. Okay. However, when you have something with a hydrogen bonder, it can vary significantly, especially if you have, if it would rather hydrogen bond to itself, it might not dissolve at all. Things like sugar tend to not dissolve in acetone because it'd rather hydrogen bond to itself. So the variability is there. But once you get to something with just a dipole interaction, those tend to be fairly soluble. And with our induced dipole, they tend to be fairly soluble as well, because your dipole can induce the dipole on your nonpolar material and allow it to be soluble. So if we get to the last stage here, if we have a hydrocarbon or a very nonpolar material, we have no solubility of ions in there. There's no driving force to let it happen. If it's hydrogen bonding, it can dissolve in a hydrocarbon if it's small enough. I mean, sorry, if the hydrogen bonding is a smaller portion of the molecule. So if you have an alcohol and a long chain, you can get it into a nonpolar solvent. However, if you have more hydrogen bonding than long chain, it will tend to not dissolve. And then dipoles and nonpolars tend to dissolve each other quite well. Okay, so what we'll see is things like acetone freely dissolves in hexanes. However, and water will freely dissolve in acetone, but water doesn't dissolve in hexanes. So, and it's all because of those different driving forces. Okay. So the last thing I want to talk about are these things called hydrophilicity and hydrophobicity. Okay, so these are things that you can trick to being pulled into water or non-water loving things by the use of their intermolecular forces. Okay, so the classical example of something that is hydrophilic is something that likes water. And so you can things like ions. So in this case, we actually have a carboxylic acid that has a long chain on it. And if it's neutral, it makes it very difficult for it to dissolve in water. However, if you make it such that you can increase the hydrogen bonding here, or even remove that hydrogen and turn it into an ion, you can get this portion of the molecule into water, but the other portion tries to stay out of the water phase. And this is how soap works, because the salt side of the carboxylic acid is actually trying to pull stuff into the water phase, and any fats or oils that are van der Waals bonded around that long chain are carried along with it. Okay, so the other side of that is what we call hydrophobicity, or fearing, water fearing, which means that in the case of this soap here, what happens when you dissolve soap into a mixture is all of the long chain, the non-polar sections, try to increase to each other, try to bind to each other, and try to push the water out. And so we end up creating these things called micelles, where we encapsulate our oils. All the ionic ends are on the outside, all the nonpolar parts are in the middle, and it can be carried away as a small fluid particle. All right, I have a question. Yeah, I answered that. Good. All right. Okay. So hydrophobicity and hydrophilicity basically is you have two strong interactions on your molecule, and you can force one or the other to do what you want it to. So if you have a strong hydrogen bonder or can make a salt out of one side of your molecule, you can pull large amounts of hydrophobic or van der Waals force materials into water. But it's not really fully dissolved. It actually forms these little clusters called colloids or micelles. Okay, so it looks like it's dissolving, but it's really a combination of two different forces. Okay, questions about intermolecular forces and how they affect how things interact with each other. Okay, so I have one last section for this, and it's all about a special case in Lewis dot structures. Okay, so I'll take a short step here to see if we can't get. Okay, so when we draw Lewis dot structures, we were taught that, you know, you take the thing that bonds the most and put it in the middle, and then you sprinkle the electrons around it, and then you have to calculate out if you have a formal charge on any atom. Okay, so when we did this, there comes a time where it's like, well, we have 4 equal oxygens here. How do I know where the charge is? Are they equal? Are they different? You know, so we can't just draw one resonant Lewis dot structure that represents all of them. So what we have in that case is what we call resonant structures, meaning we can draw more than one Lewis dot structure, and there are equivalent except for where certain bonds are. And so really not any one of these Lewis dot structures is correct, but the combination of all the Lewis dot structures are correct. So when we have a combination of different Lewis dot structures that are all correct Lewis dot structures, we call that resonance, meaning that it's going from 1 to 1 to 1 to 1 and constantly going in between all of them. Now, that doesn't mean they're all equal. It means that they all can contribute. If we'll talk about whether or not they're equal or which one is more likely to occur in a little bit. So in this case here, we have the possibility, you know, when we drew our first Lewis dot structure, we came up with this. It has all the right electrons. Every atom has 8 electrons around it. And so we think, okay, we're done. This is all of our valence electrons we need, okay? And then when we calculated our formal charge, we saw that our nitrogen had a +1, our oxygen had a -1, this oxygen had a -1, and this oxygen was 0 because it had its 2 bonds, right? That means the net charge on that molecule is -1, okay? Okay, but why did we pick the double bond on this oxygen? Okay, why can't it be on this oxygen? Well, okay, it can be. So let's draw another resonance structure that represents that. And when we did that, this oxygen no longer has that 0 charge on it. Now it has a -1. And now this oxygen has our 0 charge on it. It's like, well, okay, that tells part of the story, but we can draw another one where the 0 charge is on that last oxygen. So what this means is that each of these Lewis dot structures is correct, and that the electrons can move around, and so that negative charge can be on any 2 of these oxygens at any one point in time. Okay, so these are all equivalent resonance structures, and since the charge is the same on all the different atoms as we move from structure to structure, they are all equally contributing to the resonance of this compound. Okay. So when we do that, we've drawn 3 structures, and that's kind of hard to do. And so we can simplify that structure by saying, well, what's the combination of all 3 of these? And we're going to generate a resonance hybrid structure. Okay. So the way we do that is we keep our Lewis dot structure the way it is, But instead of having to move that double bond from atom to atom, we say that there's a partial bond that resides here a third of the time. There's a partial bond that resides here a third of the time, and there's a partial bond that resides here. So there's a partial second bond in between each of those oxygens 2/3 of the time, okay? Which means that when we look at the spreading of the charge out over those 3 oxygens here, so if it was -1 and -1 and 0, and then we move it for a third of the time, and then we move it for a third of the time, the net charge on each of these oxygens is about 2/3, a negative 2/3 charge, because 2/3 of the time, there's a -1 on that oxygen in these resonance structures. And so all of those oxygens are now equivalent, and they all have a partial negative charge on them. Notice that the charge never changed. Oh, poodles. The charge never changed on nitrogen because it always has, in each of these structures, it always has those 4 bonds to nitrogen. It always has a +1 charge. So the charge did not change on nitrogen, but the 3 oxygens on the outside are sharing that negative charge. Okay, so is that the only way to draw a resonance hydride structure? No. There's a lots of different structures that we'll see, especially when we start moving into places where we have radicals or charges or things that are conjugated. Okay, so what I mean by conjugated is that if we draw a resonance structure for this right here, and this is just a 3-carbon chain, and it has a double bond on one side and a positive charge on the other, okay? So, okay, could that be a resonance structure? Yeah, but why don't I put the positive charge there, okay? So I have to draw another resonance structure that says I can put the positive charge on that side. There's no difference between the two. So if we redrew that in just those stick figures that we were talking about, it would look something like this. The positive charge is going to go from one end to the other and one end to the other, okay? But again, because we have 2 valid resonance structures, and all we have to do is move the electrons here to take away that negative charge and make the positive charge over here. We have 2 valid structures, which means that we can draw a resonance hybrid structure by having that partial double bond, a partial double bond in between these 2 carbons and a partial double bond between these 2 carbons. And we have part of our charge here and the other half of our charge here. Because we have those valid resonance structures, it can flip back and forth, and we have what we call our resonance hybrid structure. Now, we need to pay attention to this resonance hybrid structure because let's say we want to have something come in and react with the positive charge on this molecule. Well, if we only looked at one of the resonance structures, we're only going to get one of the right answers. If we look at the hybrid resonance structure, we can say, oh, it can attack this side or this side. So I have to look at both possible products, okay? And what we'll see in these positive charges on carbon here is we'll see that they are actually sp2 hybridized and the p orbital is empty. It has an empty p orbital. So it'll end up looking something like this when you do that. That's just a look ahead, but we'll see that in a little bit. Okay, so how do we draw these resonance structures? Okay, so we have 4 rules to follow whenever we're drawing a resonance structure. First of all, we do not change atoms. Okay, an atom never moves, okay? So the position or ion, an ion can change, but we cannot move atoms, okay? So in this example here, let's say we wanted to move these electrons over to here, okay? We can do that. However, we cannot move this hydrogen to balance that positive charge. Okay, so second rule is only electrons participate in resonance. They can be non-bonded, lone pairs or radicals, or they can be pi bonds, but only electrons can move. Okay, so no atoms move. If the molecule is neutral to begin with, it has to stay neutral. If it had a positive charge, there has to be a positive charge. If it had a negative charge, there has to be a negative charge. And only electrons move. All right, so the next rule is that sigma bonds do not participate. Okay, if you have sigma bonds, they stay sigma bonds. Okay, you will not break a sigma bond whenever you draw resonance structures. However, you can move pi bonds and you can move electrons, but you never break a sigma bond. Okay, so in the case here, we cannot just break the molecule apart trying to get rid of this positive charge. Okay, the overall charge of that resonance structure should never change. Okay, so if it started positive, it stays positive. So only electrons move, no atoms move. In fact, you typically draw it so you have the same configuration, and all you're doing is moving these electrons here and charge there, so your contributor just has the charge and 2 electrons moved. Okay, so whenever we're looking at these resonance structures, always just looking for charge and electron to move. Okay, so again, when we draw these valid Lewis dot structures, you cannot have more than 4 bonds to carbon, 3 bonds to nitrogen, unless you have a charge on it. So when we're drawing these, they have to be valid Lewis dot structures before we begin. Okay. So that means in the case of this compound here, right here, we can't just move these electrons in and form that double bond. Notice the net charge on this species is the same because we have a positive charge here and a negative charge here. So the net charge on the molecule didn't change, but we ended up with too many electrons around carbon. Therefore, it's not a valid dot structure, which means it's not a valid resonance structure. Okay. So, and again, there's too many electrons around nitrogen if we moved these electrons in, because now we have 10 electrons around nitrogen. And again, that's not a valid Lewis dot structure, so it cannot be a resonance contributor. Okay. So one of the ways we use this a lot is to move ions, okay? So when we move ions, we are moving 2 electrons to the atom, toward the charge that we had, okay? So when we start about drawing the movement of 2 electrons, we've said this before, where we have 2 prongs on our arrow means we're moving 2 electrons over. If we're moving 1 electron, we only have a single barb on our arrow. So in the case of this system here, we are drawing an arrow saying that 2 electrons are moving over here, and that means the positive charge has moved to this carbon from the carbon 2 carbons over. And to move back, all we have to do is move those electrons back into that bond, giving us our charge back on our original carbon. So we have 2 valid resonance structures. The charge and electrons have moved back and forth. Okay. So that's if we're moving a positive charge. If we're moving a negative charge, that means the lone pair is typically on the atom with the negative charge. And we do the exact same thing. We're moving these electrons in to form our new double bond, but that would give us 5 bonds to carbon. So we have to break that double bond and move those electrons onto the other carbon. Okay, so we've moved a positive charge in this side. We've moved a negative charge in this side. Note, in each of the resonance structures, we had to move 2 pairs of electrons. We had to move 2 pairs of electrons on this side here because we had a negative charge coming in and then breaking of a double bond to give us our new lone pair. So when we're moving a positive charge, you typically move 2 electrons. When you're moving a negative electron charge, you're typically moving a total of 4 electrons. 2 in and then 2 out. Okay. When we only have 1 electron, that can still contribute to the resonance structure. However, now it gets a little more complicated because you can only, if you're moving 1 electron in to create a bond, only 1 electron from this double bond is going to be moved into our new bond. So we can only move 1 electron from here, and that's why the single barb. The other electron will help create that new double bond here. That would leave an electron on that other atom. Okay. Remember, a sigma bond has 2 electrons and a pi has 2 electrons. So if we break a pi bond and move one electron one way, we have to move the other electron onto the other atom. Okay, so this gets a little more complicated because we end up having to move 3 different electrons to move the resonance structure back and forth in this radical, because individual electrons are moving. Okay, so to finalize this, we're going to spend the last 5 minutes talking about how to evaluate the relative importance of resonance structures. Okay, so which resonance structure is going to contribute more to the structure? So where is the charge most likely to be highest in the system? Okay. So the first rule of this, excuse me, is that you want resonance structures in each of the atoms to have an octet. Okay, this doesn't always happen if you have a charge, okay? But if you have your resonance contributor that has the octet, it's generally making the greatest contribution to the overall electric structure, okay? It wants the octet, it doesn't want 2 separated charges, so if you can get it so that every atom has its octet, it is the most stable contributor, okay? Resonance structures which has formal charges that are minimized are more important than those with higher formal charges. Meaning if you had a structure where you had a +1, a +1, and a -1, that's going to be less contributing to one that has just a -1 because the +1 and the -1 have shared an electron to fill that octet. So in the case of, you think about it as the fewer charges possible, the more stable, the more likely it is to be a major contributor to resonance. Okay. Now, rule 3, now that we have formal charges present, it's favorable to have the negative charge on the electronegative element, nitrogen, oxygen, etc. It is more likely to have the positive charge on the less electronegative element, like carbon or boron. Okay, so if we look at that, that trend along the periodic table where we go from, oxygen, nitrogen, carbon, and boron, think of if you have a negative charge, you want to try to put it on that heteroatom, that nitrogen or oxygen. Rule number 4 is resonance structures which atoms have like charges are connected are extremely unlikely to contribute to the overall structure. Meaning that if you had a formal charge where one atom has a -1 charge and another atom has a -1 charge and they're right next to each other, then that's not going to be a major contributor because those 2 charges are going to want to repel each other. So even if you can draw that structure, it is not going to be a major contributor. Okay, so let's evaluate the relative importance of each of these resonance structures based on those rules we have. We only have 4 of them, so it should be easy to think about. So let's look at number 1 and see how good a resonance structure it is. So let's look at this first one here, okay? And first of all, this oxygen has an octet and no charge. This carbon has an octet and no charge. This nitrogen has an octet and no charge. And the hydrogens all have 2 electrons. Okay, so it's neutral. It has no charges. It has octets. So I think that's a pretty stable charge. I mean, that's a pretty stable system. Okay, let's look at the next one here. Okay, so our oxygen has an octet. Our carbon has 6 electrons around it. Our nitrogen has an octet. Okay, now we have a positive and a negative charge opposite each other. So that's not breaking a rule because that would be 2 negative charges next to each other. The oxygen has the negative charge on it, which is the more electronegative element. The carbon has the positive charge on it. Okay, so this is not a bad resonance structure other than carbon does not have an octet. So I think this is less of a contributor than the structure number 1, but it's still valid because the charges and formal charges and everything works out. The net charge on the molecule is still 0. All right, let's look at the next one here and see if it has there. Okay, first of all, we have an octet on our carbon. We have an octet on our nitrogen. We have an octet on our oxygen. Okay, so we're doing well right now. Okay, we have 2 charges, so the net molecule is 0. That's okay. But we have a positive charge on an electronegative atom. We have a positive charge on nitrogen. Okay, so that's, you know, not the best thing. It would prefer to have a negative charge there, but it meets all the other rules of octet. It meets all the other rules of charge separation, and the net molecule is the same. So this is probably not going to be as good as this one over here. I think this one's still going to be a major contributor, but it's still a valid contributor to the resonance structure. Okay, so let's look at the last one and figure out what's wrong with it. Okay, so carbon has an octet, so that's okay. Oxygen only has 6 electrons around it. That's not good. Nitrogen has 8 electrons around it, so that's good. But oxygen has the positive charge. It's the more electronegative element. It should have the negative charge. Carbon is the less electronegative element. It has the negative charge on it. That's why this breaks the rule, breaks enough rules that it does not act as a major contributor, and therefore it's not a valid resonance structure. So if we were to rank these in order of resonance contributors, this one would not be a resonance contributor. This would be number 1 as most stable because it meets every rule. This would probably be number 2 because it meets all the rules. It still doesn't have, it has the charges on the right atoms, but it doesn't have a full octet. And this would be number 3 because we have charge on an electronegative atom. Okay, so that should give you an idea of following those rules. There's a few homework problems about trying to figure out which is your stable resonance contributors. So start looking at those 4 rules and assigning those priorities. All right, we're right a little past time, I'm sorry. But I'll go ahead and stop recording and you can ask questions if you want. Stop.